In this lecture, I will teach you universal shift register, a very important topic. First, we will see why we call it universal shift register, then we will move to this circuit. So let's start with it. If a register is there that can shift the data in only one direction, either from left to right or from right to left, we call it unidirectional shift register. We call it unidirectional shift register. And if we have a register that can shift the data in both the directions, from left to right and from right to left, we call it bidirectional shift register. Bidirectional shift register. And in the last presentation I explained bidirectional shift register. I hope you remember it. Along with this bidirectional shifting, if we have the parallel loading, we have the universal shift register. What I mean by this, if we have a register in which we have the bidirectional shifting as well as the parallel loading, then that shift register we will call universal shift register. And by parallel loading, I mean the data that we want to store in the flip-flops are entered in parallel manner, or you can say simultaneously. Let's say the data that we want to store in these 4 flip-flops are 1 0 1 1. Then this 1, the MSB, is given to this I3, 0 is given to I2, 1 is given to I1, and this 1, the LSB, is given to I0, and they are stored in these flip-flops, the 4 flip-flops, at the same time for the same clock cycle. So the parallel loading is nothing but storing our data at the same time. So this will make our universal shift register. The universal word is used because all the possibilities are covered in this single shift register. What we have studied till now, the serial input, serial output, the serial input, parallel output, the parallel input, serial output, and the parallel input, parallel output are covered in the same register. Let's see how. We have the bidirectional shifting. It means we have the serial input of data as well as the serial output of data. So the serial input is there and serial output is there. And I have already told you, in USR, the universal shift register, we have the parallel loading. It means the parallel input is also possible. So we have the parallel input. Now the only thing left is the parallel output. How we can have the parallel output in this shift register? You have to know only one thing. The parallel output is not a big deal. If you can access the output of the flip-flops, here we are using the 4 flip-flops, and if you can access the output of these 4 flip-flops, this is the output, and you can see we have accessed it. A3, A2, A1 and A0 are available to us. So in that case we have the parallel output. We don't require something very special to get parallel output. You just only have to access the outputs of the flip-flop. So we also have the parallel output in this universal shift register. So all the possibilities are covered. Now it is time to move to this circuit. In this we have used 4 flip-flops. You can see D flip-flops are used, in which clear input is there to reset all this flip-flop. So this is what we do when we have to reset our shift register. We reset all the flip-flops. For that we will use this clear input, and clock is there connected simultaneously to all the flip-flops, and we are using multiplexers. 4 multiplexers are used, and we are using 4:1 multiplexers. 4 inputs are there and definitely 1 output is there. In multiplexers we have only 1 output, and in case of 4:1 mux we have 2 selector variables, S1 and S0. They are connected to all the 4 multiplexers that we are using in this circuit. I hope you remember how the multiplexer works. It is very simple. Depending upon the values of selector variables, we have our input selected. If S1 is 0, S0 is 0, out of this 4 input, this 0 input will be connected to our output. It is simply selected. If the output is Y, then it is equal to I0. Okay, and if S1 is 0, S0 is 1, then this input 1 is routed to the output. Similarly, when S1 is 1, S0 is 0, the input 2 is routed to the output, and finally when both of them are 1, the input 3 is connected to the output. So it is simply a process of selection, and we select the input by selector variables S1 and S0. That's why they are called as selector variable. We can vary them, and by varying them we will select different inputs. So let's make one table in which we will write down these things, and also I will tell you how the selector variables are working as the mode control inputs for the shift register. It is not just the selector variable for the multiplexers we are using, but they are also used for selecting the mode of the shift register, whether we want the right shift, the left shift, or the parallel loading. So let's make the table quickly, then we will move to the analysis part of the circuit. S1, S0, they are the mode control of this shift register, and depending upon their values we have the register operation. So let me write down register operation on the right. If S1 is 0, S0 is 0, then we have no change. Okay, the circuit will remain in the same state. Whatever be the value stored in our flip-flops, it will remain the same. There is no change. There is a space between no change. And when S1 is 0, S0 is 1, we have the shift right mode. When S1 is 1, S0 is 0, we have shift left mode, and when both of them are 1, we have the parallel loading. So this is the table that will summarize the mode of operation for this circuit depending upon the values of selector variables of these multiplexers. The next thing is the D flip-flop. We are using the D flip-flop here, and you must know the table for the D flip-flop. I am going to make the table for D flip-flop quickly. We have clock, we have D, the data input, and we have the next state Qn plus 1. When clock is 0, whatever be the value of D, the output is going to be the same. So we have memory. When clock is high, D is low, the output is going to be low. When clock is high, D is high, the output is going to be high. So simply, whatever be the value of D, it is going to be in our flip-flop. If it is 0, the value stored in the flip-flop is 0. If it is 1, we have 1 in our flip-flop. So we have everything now to move and analyze this circuit, and we will prove this table that how the selector variables are deciding our operation. So let's start with the first case when S1 is 0 and S0 is also 0. The input I0 is connected to the output of the multiplexer for all the 4 mux we are using here, and the output of the mux is connected to the input of the D flip-flop. You can see the output is connected to the input, and this will play a very important role here because the output is connected to the I0. So here we have A3, you can see, and here we have A2. Similarly, we have A1 and A0. A3, A2, A1 and A0 are the outputs for our D flip-flop, and let's assume the values stored in these 4 D flip-flops are 1, 0, 1, 1. Then we have 1 as the input for the first multiplexer, and it is connected to the output. So we have output as 1, very simple, and again this D flip-flop is getting 1 as the input, and from the table you can see when D is 1, the stored value is going to be 1. So we have 1 stored in this D flip-flop again, so the output is going to be 1. It was 1 and it is again 1, and the same thing will happen for the rest of the flip-flops and multiplexers. 0 is here, then again we have a 0 as the input, 1 is here, and again we have 1 as the input. and in the last case also we have a 1 as the stored value. So it is like a cycle. We are having 1, and for the next clock cycle also we are going to have a 1. That's why I have the register operation as no change, or you can say hold, when the selector variables are 0 0. I hope you got this thing, that how we are having the hold condition when both of the selector variables or the mode controls are 0 0. Now we will move to the next case when S1 is 0, S0 is 1, and we have shift right mode. So let's see. When S1 is 0 and S0 is 1, this input I1 is routed to the output for all the 4 multiplexers. I1 is connected to the output of the mux, and this I1 is serial input. Let's say if you want to store 1 0 1 1, then this 1 is here acting as our input I1. It is routed to the output, and this output is connected to the D. So this 1 is going to be stored in this D flip-flop for the first cycle. We have stored this 1, and the next very important thing is the output. You can see this output is connected to the I1 of this multiplexer. This is very important thing for the shift right operation. You are storing 1, and whatever the value stored in this flip-flop earlier will be going to the I1 of this mux, and it is routed to the output. Hence the value stored in this flip-flop is going to be stored in this one. We are shifting the data. It will be clear when we will see or analyze the next clock cycle. This one is stored in the first clock pulse. Let's say for the next clock pulse, what we have, this one is going to be here. It will be routed to the output. This output is connected to D. So we have 1 stored in this D flip-flop. Earlier we also had 1. This one is going to be here, and it is routed to the output, and this output is connected to the input. So we have a 1. This one is stored here, and this one is stored in this flip-flop. So we are shifting the data from left to right. For the next clock pulse, this one is stored to this flip-flop, this one is stored to this one, and this 0 will be stored to this flip-flop. So we require 4 clock pulses to store 1 0 1 1 in the 4 flip-flops. So this is clear. I hope that how the shift right mode is achieved in this universal shift register. The next case is when the S1 is 1 and S0 is 0, and we have shift left mode. Let's see how. When S1 is 1, S0 is 0, this I2 is connected, and you can see the serial input for shift left operation is there. We are feeding the data that we want to shift from right to left to the I2 of this multiplexer. Okay, let's say we are storing 1 1 0 0. So this 1 is fed here at I2. It is connected to the output of this mux, and it is stored here. Fine. And when it is stored here, you can see the output of this flip-flop, you can see from here, is connected to the I2 of this mux. So the value stored here will be shifted, and in the same way for the next clock pulse, the value stored in this flip-flop is stored in this one, and so on. So the last thing that we have to see is the case when we have the parallel loading. The mode control inputs are 1 1. When they are 1 1, I3 of the multiplexers are routed to the output, and this is the most easy part of this circuit. If you want to store 1 1 0 0, this one is stored in this flip-flop because I3 is our output. This one will be reflected here, and then it goes to D and stored in this flip-flop. This one is the I3 of this mux. It is routed to the output. We have one here. This one will be stored in this flip-flop. This 0 is reflected here. It is stored here. This 0, we have the output of the mux, and acting as the input to the D flip-flop, so it is also stored in the last flip-flop. So we have 1100 as the stored value, and it is happening for the same clock pulse. You just give the clock and you have the values stored as 1100 in your flip-flop. Whereas in case of shift right and shift left, you need 4 clock cycles for the storage of 4-bit data. Whereas in this case, we need only 1 clock cycle to store a 4-bit data. So this is how the universal shift register works. If you know the basics of multiplexers, D flip-flop, and also you have studied this 4 operations in the shift registers, you will get this thing easily. So if you have any doubt, you can ask in the comment section.